Exactpro is an independent software testing services provider for financial market infrastructures, delivering industry-recognized expertise and bespoke solutions for automation and testing to exchanges, post-trade platforms, and banks across 20 countries. The firm also facilitates a variety of large-scale transformation programs related to DLT and cloud implementations at these systemically important organizations. Some of the key contributors to our success as a company include relentless learning from the most challenging transformational projects in the industry, adherence to our industry-proven principles of software testing, as well as staying focused on providing the necessary growth opportunities for our people. Get in touch with us via email or visit our website to learn more about Exactpro services, and do follow us on social media for the announcements of in-person events we will participate in the next few months.
Hello, everyone. Welcome to another episode of AI Testing Talks. My name is Anna Maria, and I am your host today. I work in Exactpro, and I'm also an outreach director of our AI testing course project. If you are interested in leveling up your career or discovering ways to leverage the power of AI tools, check out our website to learn more about the award-winning ISTQB accredited AI testing course. You can check the first chapter for free by subscribing to our 1 week's trial. Co-hosting with me today and always is Exactpro co-CEO and co-founder, AI testing practitioner, Yusuf Itkin. Hi, Yusuf.
Hello, everyone.
Hello. So for everyone who just joined for the first time with our webinars, in this series of webinars, we explore AI technology and its combination with human potential. And we will discuss further on different webinars, different aspects of AI, including generative AI, AI-powered test tools, the impact of AI biases, the role of AI in software testing and in the business processes overall, and many more. And let me introduce our guest today. Today we have associate professor from York University, whose focus is at the intersection of software engineering and artificial intelligence, Professor Song Wang. Hello, Professor Song.
Hi.
Welcome. So while Professor Wang, I'm very sorry, is sharing his presentation, I would like to remind you all that our webinar is usually divided into parts. One is actual presentation, and afterwards we are going to have questions. Please submit the questions you have during the session on our LinkedIn chat during the session, so we will address them right after the actual presentation. Thank you very much, and Dr. Wang, please, over to you. Thank you.
All right, thank you. I'm gonna share my screen. Sure. All right. Did you guys have my screen?
Yes, we
Okay,
can
cool.
see it perfectly well.
All right. All right. Thank you everyone to come to the talk, and also thanks for the opportunity provided by Exactpro to have me connected with the industry people to share our recent progress. All right. So in today's talk, and I'm gonna briefly sharing our recent progress on demystifying and detecting software bugs in AI infrastructure software. All right. So before we started, let me briefly introduce myself. So I get my bachelor and master degree back to China 10 years ago, and after that I moved to University of Waterloo for my PhD degree. And then during my master and PhD study, I have a couple of different co-ops And also, I have an internship at Microsoft Research in 2018. And besides that, I also have opportunity to co-found a startup many years before. The topic of the startup is using deep learning to improve software bug detection. And then after my graduation, I actually moved to York University to start my professional career. I became an assistant professor, and this year I promoted to associate professor. All right. And then in general, my research mainly focuses on two different topics, the software engineering and the AI. And then during my PhD study, I mainly focus on using AI to improve software reliability practice. And then since I started my professional career at York University, I moved to another direction that we're using data-driven software analytics to engineering reliable AI system. For example, we develop different techniques to detect the software bugs in AI system. We develop different techniques to generate test cases, to generate the documentations, everything that we can to ensure the quality of AI systems. All right. And then in today's talk, we're gonna take one of the direction we have done, that is finding bugs in AI system, to describe how we can use data-driven approach to managing reliable AI system. All right. All right. So nowadays AI is everywhere. So AI has been embedded into almost every single direction in our life, from financial, software development, transportation, from space engineering. AI basically has been everywhere in our life. And then one of the key reasons that why AI can increase so greatly is because the availability of open source AI infrastructure software. For example, in the last few years, we can see Microsoft have open source CNDK, and Google has open source the TensorFlow, and there are also many other open source AI framework software. For example, Caffe, Sano, PyTorch, and then so those frameworks can provide a scalable, efficient service, and developer can use those servers to build a training module and deploy AI model very efficiently. So some of the open source AI infrastructure software nowadays becoming more dominating. For example, TensorFlow and PyTorch, they have become the two main player in the market. If you look at their downloadings, for example, for TensorFlow, in last week they have been downloaded more than 4 millions. And then PyTorch has been downloaded more than 80 millions, and in total, both of the two different frameworks have been downloaded more than hundreds of millions in the last few years. So the open source AI infrastructure really play a very important role to accelerating the development of AI application. So if you look at their structure, actually most of the AI infrastructure software, they're sharing a dual layer structure. So which means they have front end and back end. And then the front end API are very easy to use. They provide a different API set for users to collecting the data, to clean the data, build the module, tune parameters. And then the backend API are more fine-grained. They can contain performance optimization, hardware management. So both the front end and front end and backend API opened to developers, which gonna be very helpful for the beginner and the experts AI modules. All right, so although AI is everywhere, however, the trustworthy AI is not everywhere yet. So in the last few years, we have saw many different AI incidents, and then the AI application can go wrong, so result in very serious consequences. For example, the incorrect prediction, flawed results, and also some financial loss, which can stretch our human life and finance. All right. So, okay. So if you look at the reason why those AI module goes wrong, there are a lot of different root cause, including the errors in the data, errors in the module, and also another big reason is because the AI infrastructure is not reliable. Some of the API in the AI infrastructure cannot deliver the expected output the user wanted. So this also going to be the focus of our work. And then, all right, so our recent work on taming the AI infrastructure bugs, starting from understanding what kind of bugs are there in AI infrastructure. So we're focused on AI security vulnerability specifics as they're going to have a big impact. So this piece of work has already published in MSR 23 last year. All right, and then after that, we try to explore whether the existing bug detection, fuzzing techniques can be applied to AI infrastructure. So we actually want to see whether the widely used static analysis, for example, Facebook inferred, Google ever pronounced those famous static analysis can work on the AI on the security vulnerability from AI infrastructure. All right. And then after that, we propose our new fuzzle tools for detecting AI bugs. We call it history-driven fuzzle for AI bugs. All right, and then another research line, we also look at whether we can leverage a large language model to accelerate the bug detection in AI infrastructure. Specifically, we look at Miss API user detection, the machine learning, deep learning, check bug detection, and also regression testing. All right. Okay, so I'm gonna start from our first piece of work, the understanding the AI security vulnerability. So, and then in order to understand what kind of security vulnerability in AI libraries, the first thing we need to do is to select the libraries we want to analyze. So we do provide a different criterion. For example, the library should be popular, widely used by many different domains, and also the library should be maintained for many years. Otherwise, we cannot have enough data. And then we also want to the library cover more different sections from, for example, starting the library can provide API to help user training the module, testing the module, optimize the module, right? And then we also want the library can provide a state-of-art algorithm regarding classification, clustering, and then prediction modules. All right. So as a result, 7 open source library has been selected. For example, TensorFlow, PyTorch, sklearning, MLPack. Those are very popular machine learning libraries. So the next step is to collecting the vulnerabilities. At the very beginning, we actually look at the National Vulnerability Database. We want to see how many of vulnerability from those machine learning, deep learning library has been archived in the NDV, the National Vulnerability Database. So what makes it a surprise is that we found that most of the vulnerability in the deep learning frameworks were not reported or carved in the National Vulnerability Database. So if you look at the table, you can see that only TensorFlow have 33 vulnerabilities carved in National Vulnerability Database. So this actually posed a challenging task for us. We have to find a way to collecting the data. And then what we did here is that we actually found a heuristic-based approach. So what we do is we look into the commits. So most of the project have a lot of commits, and then if you look at the commits, sometimes the commits title gonna include the reason why the users developer makes the commit. For example, we look at the keywords regarding fixing vulnerability, regarding fixing non-point exception, buffer overflow, those kind of keyword-based approach. So based on our keyword approach, we actually, first of all, we find more than 5K commits that are potentially related to vulnerability fix and detection. And then we also did manually verify the result. We have 683 vulnerabilities left in our dataset. So for each piece of the vulnerability, first of all, we're gonna manually check their code, check the reason why the vulnerability happened, and then we also look into their root cause. Also, we check the this symptom and fix pattern, how developer fix the bugs. So at the results, we summarize different reasons for their CWE root cause. We also map each vulnerability to different CWE types. We summarize the symptom and also their fixed pattern. So yeah, so the taxonomy here actually show the CWE vulnerability type in the deep learning libraries. So you can see in total, we summarize the vulnerability in deep learning library into 5 different categories, from memory error to numerical error, buffer error, resource error, concurrency error. So different from traditional software, we find a lot of them actually focus on memory error and numerical error. So this is going to be very easy to highlight the difference, right, from deep learning library and traditional software. If you look at traditional software, the major CW type will be logical errors. However, in machine learning libraries, logic error will be a very minor sense. Okay. And then regarding the root cause, we also found some interesting things. So the dominating type in the root cause is data type issues. The reason is because if you look at the deep learning frameworks, they do have a special data type. For example, TensorFlow have tensor. The tensor is a very important special data type. And then there are also many other different data types, specific data type in deep learning frameworks. And then a lot of the root cause is because the developer or user did not handle the data type correctly, and then result in a lot of vulnerability related to data type. And then we also build a root cause and the map from root cause to symptom. For example, we found that if the root cause is memory error, is gonna have symptom like resource consumption, crash, or segment fault. And then regarding the fixing pattern, we also manually check how developer actually to fix each vulnerability. And then we also find that different from traditional software, so most of the vulnerability in deep learning framework do not need a very complicated fix. On average, 5-line fixing is enough for fixing deep learning vulnerabilities. And then most of the fixing regarding checkers, for example, add a checker for different data properties for overflow, for non-point exception. And then this is also very different from traditional software. All right. Besides that, we also did a comparison between machine learning software and traditional software. So if you, I only pick 2 important things here. You can look at the paper for more detail. So if you look at the root cause in traditional software, the main reason for the main category of root cause is memory related, and also sometimes the user developer propose new features. The new features can also introduce different vulnerability. So those are the 2 main reasons for the root cause. And then, however, in our study, we found that the 2 main major root cause are memory management and the data type. Again, as I explained, because deep learning have different data structure, different paradigm compared to traditional software, so the root causes are also different, and also the symptom are different. In traditional software, and the 2 major symptoms will be performance issues and incorrect functionality. However, in deep learning framework, we found that the main symptom are directly the program gonna crash, all the program gonna have take much more resource. All right. And then, so this piece of work actually unfolded a new direction to understand what's the difference between deep learning framework and traditional software regarding the vulnerabilities. For example, what are the type of vulnerability in deep learning software? What are the root cause? What are the fixed pattern? So this is the first study on this specific domain. And when we got the security vulnerability, the next step is we want to know whether the existing vulnerability or software bug detection approach that widely used in traditional software can apply to machine learning or AI software. All right. And then what we do here is, first of all, we look at the static analysis. So this is the common procedure of static analysis. So when you get a source code for static analysis, often we're starting from source code, and then we do code parsing. We're using different representation to represent the code. The representation can be token level, API call graph, or syntax tree, or even count flow or data flow, more complicated. And then there are also a different set of a checker. The checker here are going to be the rule-based checker. For example, non-point exception, right? So you're going to look at the whether the vulnerable variable going to be involved before sign initialized, right? So there's going to be a non-point exception. So after that, we're gonna analyze whether there's a vulnerability or bug. Okay. So this is the procedure of static analysis. And then, so if you look at how the vulnerability in deep learning framework exploits, things are different. So most of the TensorFlow PyTorch library contain the client's code and the backend code. As I said before, there's a front-end API and a backend API, right? So sometimes the backend API are C code, but the front-end API are always Python code. And then if you want to explore a vulnerability in deep learning library, we have to, first of all, we need to create a malicious data. And then the data often input from the Python client code. For example, here we have a malicious code. The code is input from API call in the front end. And then eventually we're through the intermediate layer, we're going to go to the backend. For example, in this example, there is an integer overflow. So this error actually caused by different integer types, all right? So in order to explore this error, we have to create a data from the Python client, and the root cause actually back in the backend of the C code. Okay, so so you can see the difference between the traditional software and deep learning machine learning library. For the traditional software, often we only have the C code, we only have the Java code, but here we have both Python code and C code. So we need to find in order to conduct the research, so we need to find tools that only support the C vulnerability detection. All right. So as a result, we find CPU checker, Facebook Infer, Client, Flow Finder, and the rest. All right. So and then regarding the deep learning libraries, as I said before, we only focus on the libraries that contain the C and C plus component. So as a result, we only have MOPAC, MNest, and TensorFlow and PyTorch. All right. Okay. So when the static analysis tools and deep learning framework has determined that for the next step, we want to look at how well those static analysis tools perform on the deep learning vulnerabilities. So remember, we have more than 600 vulnerabilities in our first study, and then we pick a full 100 from those initial dataset that only contain C libraries. So there's 43 CW types across the 400 vulnerabilities. So what we do here is that given the vulnerabilities, we're starting from their fixing commit. So if you look at the commit message, you can figure out the fixing commit, and then we got the code before the fixing commit and after the fixing commit. So we consider the code before as the buggy code, all right? And then we apply the static analysis tools to the buggy code and to see whether we're gonna generate the result. We're gonna find the vulnerability in the buggy code, all right? So remember, so sometimes the buggy code can be very can be cross different chunk. So we also propose different way to match the reported results and the ground truth. And after that, we also do a manual analysis to ensure our results is accurate. All right, so let's look at first of all. So we show the vulnerability reported by static analysis and the vulnerability in our dataset. In the left side, you can see here actually the distribution of vulnerability in our dataset. And then if you look at the CWE type, the dominating type it will be integer overflow and race condition and mission release memory. So the top three. However, in the reported vulnerability by the tools. In total, there are 138 vulnerability reported by the tools. And then if you look at their vulnerability types, you can find that the dominating type are buffer overflow and static-based buffer. Both are buffer overflow. All right. And then there's a mismatch between the bugs, the vulnerability in real world dataset and also reported by the tools. Okay, so in the next step, we want to see what exactly bugs that can be detected by those tools. So one thing I want to emphasize here is even the tool reported 133 vulnerabilities, not all of them are true bugs. A lot of them are false positive. Okay. So and then we further look at each of the vulnerability reported by the tools. What we do here is we manually check whether the bugs reported by the tool is actually a true bug or false positive. As a result, we found that if you look at the table here, we presented the performance. So among the 5 examined tools, 3 of them can only detect the 0 vulnerability. For example, CPU checker, Facebook infer, cloud static analysis, they actually detect nothing. And then only 2 of them can detect several bugs, Flow Finder and IITS. They only detect, in total, they detect 9 different vulnerability, but if we remove the duplication, only 4 left, which means among the 400 vulnerabilities from the real-world machine learning libraries, only 4 can be detected by the widely used static analysis tools. All right, so we do find the gap here. So which means most of the static bug analysis cannot use to detecting bugs in the machine learning library. All right, and then we further analyze the tools to see, okay, so what the reason why they cannot detect the vulnerability, cannot detect the bugs in those AI infrastructure software. So we summarize the reason into 3 big categories. First of all, there's a natural gap between the 2 different types of software. First of all, the logical flow in the static analysis are built on traditional software, right? So basically are logic errors. However, in deep learning framework software, the logic error are different. The logic error can relate to the data process, can relate to the module building, performance tuning, parameter tuning. So there are different logicals among traditional software and deep learning software. And then the second reason is that most of the static analysis tools do not have a well support of machine learning specific constraint. So one of the specific type is there's no support for data type. For example, as I said before, the tensor is a very important data structure in TensorFlow, and a lot of error, a lot of vulnerability actually related to the invalid or incorrect operation on tensor. However, if you look at the static tools, none of them can support the checker on tensors. And then the last reason is because of a lack of semantics for machine learning code. So when you want to scan code, we need to check both the non-deterministic and deterministic behavior of code. However, most of the static tools can only check the deterministic behavior, but machine learning code has a lot of non-deterministic behavior, which is out of scope of the static analysis tools. So in a summary, to detect machine learning vulnerability, the tools need to focus on understanding the nuance of AI modules, data, and the process. Okay. All right, and then we also give out different strategy to improve the tools. To improve for general software, we can extend the input representation, enhance the detection rules, and also for the machine learning framework, we suggest the existing tools builder to provide support for machine learning type checker, computation graph support, and also cover more different type of APIs. And then from another domain, we also want to um, suggest the developer consider using LLMs to help detect the bugs, directly using LLM as end-to-end bug detector for deep learning frameworks and traditional software. All right. So after that, after we figure out that static analysis cannot help detect the AI infrastructure bugs, for the next step, we turn to the fuzzy testing. All right. We want to check whether the fuzzy testing technique can help us detect the bugs in the AI infrastructure software. All right. And then to start the work, first of all, we did a survey. We searched the papers on detecting bugs by using Fuzzle, including the Fuzzle framework for both traditional software and deep learning frameworks. So there are many different Fuzzle papers in the history, and then we pick several of them as our baselines. All right, and then here, this is the procedure of deep learning fuzzles. At the very beginning, most of the fuzzles share the same paradigm. Every beginning, they're always starting from code collecting. So fuzzle means you want to generate a malformed input, right, to trigger the bugs in the API. So first of all, we need to figure out what are the APIs. And then the API can collect from the documentation, from the library testing, from deep learning module. As far as the involve API, we can use the API. And then after that, we need to do the code instrumenting. We need to figure out what the input scope, what is the parameters space of the API. And after that, we're gonna do mutation. We generate the code and then mutate the input values. And then we're gonna run the code to check whether the mutated code can actually find the bugs. And then there are three type of different oracle to help check whether a bug is found or not. The first one is differential testing. So for deep learning libraries, there's a unique sense. Most of the deep learning module can run on either CPU or GPU, right? So for the differential testing here is we're gonna compare the results from running on CPU and running on GPU to see whether the results are similar or different. And then another oracle is we're gonna directly check whether the code is crashed or not when you run the code. And then we also have a metamorphy testing. For example, if the API gonna run slow or faster when you change to different data type. Okay. And then we also found that there's another type of deep learning funnel that is a larger language model based one. So in this type of funnel, they directly input the code into LLM and ask LLM to generate input values that can trigger bugs in the given machine learning API. Okay, so those are the paradigm of the two different type of deep learning funnels in the literature. So what we want to do here is that we want to examine the performance of those two different funnels on real world software vulnerabilities from AI infrastructure software. Okay. So yeah, so we want to know how effectively those two fuzzle can find bugs in practice in the deep learning AI framework. Okay. So first of all, we need to collecting the benchmark dataset. So as we already done in our prior work, so we directly get the data from our previous study, and then after that, for each of our API, we're running the fuzzy tools to see whether the fuzzy tools can actually find the bugs or not. All right. So in our previous study, we focus on we already collected a lot of many different vulnerabilities, right? However, not all the bugs, not all the vulnerability are detectable for Fuzzle. So if you look at how Fuzzle works, so we can find that Fuzzle actually, first of all, Fuzzle gonna generate incorrect input, and then they're gonna use the input to drive API, right? So a lot of bugs that are not detectable can fall into the category here. So, for example, the bugs that are specific to certain platform. For example, a lot of bugs are only can only happen on Windows or Android, so we exclude those bugs. And also, some of the bugs require devices, for example, GPU and CPU. We also exclude those bugs. And then in total, the results, we only have 412 bugs left in our dataset. Okay. So each of the bugs, so in order to see whether the fuzzer can detect them, we'll generate one thousand different tests for each API, and then in total we spend 60 different CPU days to further testing all the API from the two different library, PyTorch and TensorFlow. All right, so here you can also see the type distribution in our database. All right, and then so this table actually show the detection results of different fuzzles. All right, so final thing here is that you can find that the traditional fuzzy, for example, free fuzzy, deep rail, and knobless fuzzy, they actually detect non-vulnerability in most of the versions, all right? And then the direct approach, LM-based approach, Titan fuzzy and fuzzy GPT actually can detect more bugs than the traditional approach, right? So which means simple LM-based approach can actually perform better than those complex conventional fuzzies, right? So so the summary for this paper is that we found that fuzzy tools are very limited in handling the complex and data dependency nature of deep learning frameworks like TensorFlow and PyTorch. The current fuzzy cannot help us to detect the real world software bugs and vulnerability in deep learning frameworks, right? All right. So I will also go into detail, go into deep to show what are the major reasons for mission detecting so many deep learning bugs for the fathers. And then we'll also summarize the reason into three big category. First of all, we found that those fathers cannot support different API usage context. For example, the fuzzy we examined, most of the fuzzy lack support for multiple API usage patterns, and then they cannot create the essential environment for core API. And then the second category is the text input generation. We found that most of the fuzzy cannot support very complex data structure generation, and also only focus on very limited type of data. For example, they only generate data for integer, double, string, those very basic type. They cannot cover special data type in TensorFlow, for example, the tensor and also turbo different type of data. And then the last reason is because most of the further lack of modeling deep learning pipeline. So deep learning module are different from traditional software. So to build a module, you have to starting from data collection, data cleaning, model building, training, and performing evaluation, right? So However, most of fuzzle cannot generate those pipeline code to test a specific API, right? So I think the reason is because the fuzzle basically most of the fuzzle we examined lack the domain knowledge of machine learning. Right? So for example, they don't know what is a usage API, they don't know what is the data type, they don't know what is the deep learning pipeline. Motivated by this, so we propose a history-driven fuzzle for API for detecting API bugs, right? So look at it on the figure here. What do we do exactly is we're actually looking back into the full 100 vulnerability we analyzed. We look at the vulnerability one by one. We found some very interesting patterns. So for example, in this one, this is actually a bug in TensorFlow. The bug is caused by mission validation, right? In undefined behavior in the sparse tensor denser. All right, and then developer also already provided code why the bug was happening. And then by looking at the example code, we found a rule. The rule here can be used to generate specific domain-specific rules to fuzzy deep learning framework. All right. So we mining the 400 vulnerability. As a result, we generate 18 different input rules for fuzzy. All right. So most of the rules are covering different aspects. For example, the first one we show here is actually cover the dimension mismatch of a tensor. And then we also have the rules regarding generating very large values. And then we also have the rules to use the specific type of data in TensorFlow. All right. And then by using the rules, we can have to generate domain-specific input for deep learning library. So we actually examine our fuzzy tools. First of all, we examine our tools on knowing bugs. Remember, we have 400 bugs, right? So first of all, we give it a name. The name of our tool is Orion. So we run Orion and three baseline approach on the knowing bugs. So we find that Orion can detect the largest number of knowing bugs compared to static art approach. And then we also run our approach on the new latest version. We want to check whether our Orion can help detect a new vulnerability or new bugs. As a result, we detect 135 new bugs. And then, so although most of the bugs we detect are vulnerability, uh, but for but for now, only 6 of them get a CVE ideas, and most of the others are still in the process to get a CVE. So when the process of getting CVE is when you find the bugs, we report it to the developer, and then the developer gonna report to National Vulnerability Database, and then the NVD gonna assign a CVE. So the whole process is gonna be very long. For now, we only get a 6 CVE. The left are in the process. So you can find that our approach, although very simple, we find the rules from the history bugs and we directly use the rules to generate input. However, the input can help us find the deep learning vulnerability very efficiently compared to existing approach. So, all right. So here I show and confirm the bugs that are detected by our pattern. So the root cause of this vulnerability is because when you use a very large value, integer value, as a dimension of a tensor, for example, here, we're using a very huge integer value as a dimension of tensor, and then the program crash. All right. So we reported the error to um, TensorFlow, and then the developer confirm, okay, this is actually true bug, then also propose how to fix the bugs. And then the bugs are already fixed in TensorFlow. Okay, so above all, I mainly introduced how we can understand the AI security and whether the traditional approach works for AI security vulnerability detection. And based on our funding, we also propose a history-driven fuzzle for AI bugs for detecting AI bugs more efficiently. So on another side, we also work on using LLMs. As you know, LLM is now a big thing, a main thing in the community. Everyone say want to use LLM to facilitate a specific task. And then we also look at whether we can use a large language model to help us detect the bugs. All right. For example, we have proposed LLM-based bug detection for API misusage. We also have proposed LLM-based bug detector for checker bugs. And also we are working on the LLM-based regression testing framework for now. All right. So yeah, as I said before, nowadays LLM has been used in many different domains and also in automatic software engineering domain. So with LLM, so users can directly encode it a prompt and then the prompt can include both natural language description and the code. And then the prompt can be can ask the LLM to generate the solution. For example, if you give a piece of a code and ask LLM to generate the test code, you can also give a natural language description and ask LLM to generate the code. And then sometimes you can also give a issue report and ask LLM to generate the patches. So, so what we did in this research line is we want to understand whether LLM can also help us to detect the bugs. Okay. All right. So in this study, we focused on the deep learning API misuse. As there's no prior study, so we first of all we conduct human evaluation. We actually collect more than around 900 API misuse from TensorFlow and PyTorch, and then we manually clarify the bugs into different categories. For example, what is the type of misuse, what are the root cause, what are symptoms. And then after that, we also want to compare what's the performance of traditional approach, right? So if you look at the traditional approach, for example, TADAF is one of the most widely used traditional API misuse detection. So actually, TADAF starting from documentation analysis, you're gonna analyze the documentation, collecting the API, and then the mining the pattern, how API gonna be used. And after that, TADAF will summarize the rules regarding API misuse. Based on the rules, TADAF going to be used to detecting errors, right? So if we directly apply the traditional API misuse detection to deep learning library, we have the following challenging. First of all is the context, right? So the traditional software are different from machine learning, right? So the contexts are different. And then we also require expert judgment to help us summarize the rules. And also we need an expert to create the rules. So those are challenging of TDAF. And then to solve the challenge, we tend to LM for help. So because for the code generation, we can directly use LM to understand the code. And then for the rule understanding and creation, we're directly use LM to reason the rules and create the rules for for API misuse detection. All right. So based on what we found, we actually propose a framework named LM API detection. We're using LM for API misuse detection. So in the first step, we're actually first of all, we collect the API misuse from the history data, and then we do the misuse rule extraction. Where in this step, we're directly using LM to help us to generate the rules. So this is the prompt we actually input into LM. For example, we give a piece of a code, and then we ask the code to summarize what the patterns in the code. And then after that, in the second step, we're using LM to understand the code and summarize the main idea of the code, summarize the semantic information of the code. So this is actually the prompt we give into the LM. And then after that, we also use LM to detect whether the code actually violate our rule dataset. So this is the prompt we give to LM. We give the code snippet and we ask the LM whether the code snippet actually violate any of our existing dataset. So as a result, we also, when the API misuse is detected, we also ask LM to propose a patch to fix the misdetection. All right. So here we show the prompt how we're gonna ask LM to fix the bugs. Okay. So here we actually show the LM based API misuse detection actually perform better than the traditional approach TADAF. If you look at first of all, we examine the performance of our approach on the 891 confirmed API misuse detection. We found that our approach can detect among 60% of bugs. However, TADAF detected nothing. So we actually perform better than TADAF. And then in the second step, we also want to see how well the LM-based approach can repair the API misuse detected. So we can also find that our approach also outperform the traditional approach. All right. Okay. So yeah, so here as an example, we show that by using LM, we can actually improve a lot of different traditional software development assurance tasks. For example, API misuse detection is one example here. Okay. So looking to the future, we want to incorporating LMs into more software AI reliability efforts. And then I think that there are two more promising directions. The first one is fine-tune LMs. So this is here we actually show a work. This work has been published in ISTA this year. So what we do in this work is that we find that if we fine-tune a small LM, it can perform better than state-of-art larger LMs. For example, in this work, we actually fine-tune Code T5. Code T5 is a very small large language model. Its parameter size is only 200 million compared to 100 billion of GPT-4, right? So this one is really small. So we collecting the data from widely known dataset to fine-tune Code T5 to let it generate test cases for a given project. And then we found that if we fine-tune Code T5, so here Code T5 with domain adaptation, we mean domain adaptation is a specific type of fine-tune. So we found that when we fine-tune Code T5, the performance can increase semantically, for example, significantly from 20% to 95% on passing rate. And also the performance of compile rate and below all different metrics have been significantly improved by using fine tune. And then on some of the metrics, the code file with domain adaptation can even outperform GPT-4 on test case generation. So this actually show the great potential of fine tuning on the small logical model rather than directly using the state-of-art large language model. Okay, and then the next direction I want to mention is that the RAG. Instead of using fine-tune, RAG will be another good solution for test case generation. So in this paper, we actually examine the performance of RAG on test case generation for deep learning frameworks. For example, we focus on test case generation for TensorFlow, PyTorch. And then what we want to do is that we want to examine different resources for RAG. So for building a RAG module, you can choose different resources. For example, the resource can be API documentation, can be issues in GitHub, can be Stack Overflow, right? So we want to see how helpful different resources can help us generate test cases. And then in this study, as I said before, we focus on the test case generation for deep learning infrastructure, TensorFlow, PyTorch. And then at the result, we found that using RAG, we can actually improve the performance. You can even generate better performance than GPT-4. And also, the different resources have a different impact. So the GitHub issues can have actually benefit RAG to generate more useful test cases to help us find more bugs. And then we also look into the reason why GitHub can help us why the rag build up on GitHub can help us find bugs. The reason is because if you look at the GitHub issues, there's a lot of common cases that provide exactly input that can trigger API. For example, in this example, um, we find that the code in the GitHub issue directly mention how to trigger an error. So our general test case is directly copy the input value from the GitHub issue and help us cover more code to detect more bugs. Okay. All right. So yeah, those are the two directions I want to mention. Those gonna be the I think those fine tune and RAG will be the next big things in LLM for software engineering development. Okay. So overall in this talk, I first of all, we briefly introduced how we analyze the vulnerability in machine learning libraries and how well and how bad the traditional approach perform on deep learning libraries. And also we propose a history-driven fuzzy deep learning framework. And then after that, we also introduce how we can use an LLM to accelerate the software quality assurance tasks. And then I also give two different directions for the future work. All right. So thanks for listening to my talk. I'm welcome if you have any question. Thanks.
Thank you. Thank you, Professor Wang. What can I say? I've tried to count how many research papers have been included in this 57 minutes talk, and it's about 6, right?
Yeah, I try to include as many as we can.
Yeah, thank you very much. It looks very impressive, and I believe that it's a bit difficult to really understand deeply of every slide that you've been saying. That's why I'm just first of all, before we proceed with the questions, would you be so kind to provide the list of the articles, the research papers that you've been mentioning during the talk? So maybe in a chat, or you can share it with us, so we will share it with everyone who's been listening.
Yeah, I think
That's very interesting. And yeah, probably I saw some links that you've been. Ah, yes, relating to. Yeah, okay, then we will share with everyone who've been listening in a chat in some time after the webinar. Thank you very much. So I think that one of the research that the papers that we have been mentioning very much applicable for practitioners who are listening us now, maybe API misuse and your talk about RAG around the work that you've been doing around RAG. So we'll definitely share it with everyone. Thank you. So we're waiting for the questions in the chat, but maybe we can start first. Yosef, do you have any questions?
Yes, sure. Thank you very much, Professor Wang. As software tester, so I get excited when I see the words test Oracle. So, and on deep learning infrastructure frameworks, you mentioned the main oracles, so there is no crash, that the data is identical between CPU and GPU,
Yes.
and also the speed of execution. Do you have any data, or have you ever encountered data that describes how known defects are related to these oracles? So how frequently they can be detected by this particular oracles?
All right. Yeah, that's a good question. So the differential testing, we observe some cases, but not too many. The reason because we have to create a very complicated module. Otherwise, we cannot trigger, for example, only as common cases that contain very complicated procedure can trigger this kind of Oracle issues. So most of the code we observe their results are similar, either CPU or GPU. Yeah, a lot of error have the Oracle crash. They're gonna directly crash if you call API, so you cannot input a correct input, and then they're gonna directly crash. That's the major Oracle we observe in our testing procedure. Yeah.
Do you think when one considers creating testing solutions around infrastructure libraries, what is preferable approach? So more direct when we are trying to create something that uses API, or instead try to create some uh, integrated solutions that involve so not just API level, but also some I would say dummy AI program that is trying to use the infrastructure framework. So whether it is better to try to use API directly or try to have a program that will be responsible for calling this API. So
Yeah,
it is.
Yeah, so from the texting API perspective, I think involve more dummy code would be better because you're gonna cover more corner cases. So I think the most efficient way to find a bug, so testing API, is to using API from uncommon scenario in an uncommon scenario, right? So when the API was developer by developer, and they always testing how the API used in a common scenario. But sometimes the API gonna crash. The error gonna happen when you test use the API in an uncommon scenario. That's I think a good way to test in the API. But from the user perspective, if you want to build a module, it's better to directly call the API.
So, the number of most popular frameworks is two, so by TensorFlow and PyTorch. So the question here is, do you think this most of the obtained observations, are they more related to the nature of deep learning, or they are more I would say overfitted to particular these two particular frameworks. So when
Yeah,
you explore the differences between traditional code and this particular code, is it more the nature of the domain, or it is just specific of these two particular implementations?
yeah, I think both are involved. And then if you look at TensorFlow and PyTorch, they're pretty similar. Even TensorFlow and PyTorch are pretty similar. So a lot of people use TensorFlow as because TensorFlow is their first library. There's gonna be learning gap between you switch from one library to another library. And then another reason is because I think TensorFlow and PyTorch in general have a better support than other libraries. So for example, TensorFlow and PyTorch, their library has been evolved very quickly compared to other libraries. They can support state-of-art modules. Uh, but a lot of other library, for example, sklearning, and then they only support very traditional machine learning modules. If there new module, let's say, developer from academic, TensorFlow and PyTorch can quickly support the module, but sklearning or other libraries, they might take quite a long time to build the module. Yeah.
But the PyTorch was developed in 2018, or
Yeah.
and on your line on your tiny line, but there are, oh yeah, 2017.
Yeah.
But afterwards, there's supposed to be some developments, right? So, but nothing goes in comparison with these two frameworks, right?
Yeah. So I didn't list out. There's a lot of other open source AI infrastructure, but not as popular as TensorFlow and PyTorch. So TensorFlow and PyTorch are still the top two now. So if you look at the downloads, PyTorch has been downloaded 8 million in the last week. So already dominating the whole domain here. There's a lot of other infrastructure from the commercial company, for example, Apple, Amazon. Also, there's a lot of other company. They also have their own, but they're not open source. So I didn't list it here. Yeah.
Right, exactly. So
Is
we need
there
to
any
remember that it's
reason why there is no new open source frameworks, or say all required problems were addressed already by PyTorch and TensorFlow, so there is no need to have anything new or reinvented?
Yeah.
Okay.
Cool.
may I interfere? So I understand. So the first the questions from Joseph probably will be more technical side, but let me go back a bit to the basics. And in terms of taking into account your background with deep learning systems, can you give us a simple explanation of the main differences between conventional systems and deep learning systems, if I may? I understand that there was some slide with comparison of the framework, as I understand, of a deep learning framework and conventional system, but there was no, I think, comparison between the system that is using deep learning frameworks and the conventional system. Is there any so first question is the main difference, and the second one is there the difference between the system that is using deep learning framework and the actual deep learning framework, the parameters?
That's an excellent question. Yeah, so to be precise, I think there are three different types of system. One is traditional software, for example, Linux, right, and Firefox. Those are very traditional software. So they're basically built on C, and there's no machine learning module inside. And then there's also another type as we call AI, AI powered software. For example, if you're using Amazon, there's a recommendation system, right? So the recommendation system is kind of a traditional software plus AI modules. And then there also AI infrastructure as what we studied here. So here we only compare traditional software with AI infrastructure. The reason because there's no study on studying the characteristic of AI module inside the software. For example, the AI powered software is pretty emerging since. Even the AI infrastructure is also very emerging since there's not too many study on those domain. We actually take the initiative to study their characteristics. So if you look at the vulnerability at the very beginning, we said here, there's not even people are not even reporting the vulnerability into the MVD. They're not following the practice of handling vulnerability. So there's a lot of gaps to fill. And then in this study, we actually only focus on comparing traditional software and AI infrastructure. So regarding the difference, so traditional software, they're more deterministic. They have a lot of data counter flow, for example, if and else. If you input this, you can output that, right? So it's more deterministic. But AI software are more non-deterministic. They're learning, they're data-driven, right? So the outcome actually depends on the data. It depends on what kind of input you give it, right? So it's more non-deterministic, and also there randomness inside. For example, the neural network, right? So the neural network, deep learning network, they're basically non-deterministic. So that's I think the main difference. One is more deterministic, one is more non-deterministic.
Thank you. In terms of from the software testing perspective, there was study more to the end of your presentation where you've been sharing the test cases. So the previous one, the testing of non-deterministic system, so deep learning system. Do you have any example of the test case? Probably it's supposed to be a bit different from the conventional system overall. Maybe there is any slide or.
I think I'll show one but later. Yeah, for example, here.
Okay.
Yeah, we show test cases how we find the error. So the error here is when you have so the tensor is a very complicated data structure. Tensor can have its type, its dimension. For example, here, tensor dot, right? So there have 3 different arguments. The last one is the dimension. Tensor. Let me use a pen. So the last one is dimensional tensor. Originally, the developer did not test the scope of dimension. And then if we input a very large dimension, this is going to be outside of the integer range. And then when you call the program, it crash. So this is the test cases why we can find the bugs.
Yes, but what is the main difference between the test cases for the conversionals, for the traditional system and for the deep learning one? Is there any parameters or
Yeah,
specifics?
We also have some others, but I didn't show here. Some of the vulnerability can also only be triggered when you input a specific training data. When you train the module on specific data, you can have trigger the errors. As I said, the error is when you perform the module on CPU and the GPU, you're gonna have a different performance. Yeah, so their API implementation have different behavior when on different hardware.
Got it. Got it. Thank you. During the research, I understand that you have an openly storing the bugs that you found during all the research, or maybe it's only related to one type of the research, API misuse, or maybe maybe it's only one link. Do you have any particular interesting finding among the bugs that you found identified, or they are all the same, similar type?
Oh, they're covering different APIs. The misuse here, I think, every single misuse that we detect, I think, are different APIs, but we didn't see whether their scenario are similar. We only check whether users actually use the API correct or not.
Okay, right. I thought that you're going into detail and see the actual scenario. That's why I've been asking that. And I have a few more questions. Yes, if you want to continue, I can stop here for now.
Sure. So we have a question from LinkedIn from another software tester going back to oracles. I will probably rephrase it a bit. So on using LLM in software testing and also looking at your presentation, would it be fair to say that there is more work, more data available and more research going into developing inputs for the scenarios rather than trying to produce oracles? So it looks like the oracle product is substantially more complex.
Yeah, that's true. I think the main task challenging here is to generate the input value rather than the oracle. The oracle is pretty straightforward. How we're gonna reach a specific oracle gonna be the most challenging things.
But oracle is straightforward for a limited number of cases, like if you have a crash, or if we have immediate simple discrepancy between running on 2 different types of hardware. But developing Oracle for anything else can be a more challenging
Oh,
task?
so yeah, I'm sorry, I understand you. So for further testing, we actually don't care the oracle. We generate the code and run to see whether it's crash or whether the code have different behavior on different platform. For in general testing, Oracle is still a big challenge, even with the help of LM. I think we're still far away from solving the issue. Oracle is still a bigger challenging because if you don't know the ground truth of the logic, we're not be able to figure out the Oracle. Yeah. For further testing, we actually skip the Oracle part. Because further testing, we only want to know whether the code is crashed or not. We're not gonna see whether the code gonna output the expected results. Yeah.
Yes, you're very happy with the with the answer. Okay, I have another one related to the very first slide. So you have been showing your research path, which ends 2018. On 2018, we have at least 6 missing years in your career path. Probably they have been fulfilled not only with academics, but maybe with some practical things. So do you have any stories of applying all your research that you've been sharing so far in your career path? And maybe you could share some stories with companies that you can tell, or you can you can hide the name of the company.
Yeah, so I did create my own startup during my PhD study. So what we did here is we were building the first deep learning based bug prediction. So given a piece of a code, we try to predict whether the code is clean or not, what kind of bugs it contain. At that time, I think the main challenge is the conventional deep learning framework are not capable to given the reason to explain its prediction results. For example, we predict a piece of code as buggy. However, we're not able to explain why it's buggy. What's the reason? So that's the big challenge for our work. At that time, we connected with a lot of industry company, for example, IBM, Microsoft, even Amazon. So we provide our tool, run our tool under the code. However, we cannot explain the results. And then later on, because we do not have enough funding, and then also I moved to York University as an assistant professor. So the company just stopped.
Yeah, about bug prediction, I think that is very important part of the
Yeah, so
testing process.
when we talk
It's a
with the
shame.
developer at that time, everyone want to know if you tell me the machine learning actually work, you need to explain why it works. You need to give it a reason. If you predict something as buggy, you predict something as vulnerability, you need to explain why it's buggy. Also for test
Exactly.
case generation, we also need to providing the test plan why you generate test case this way. So a lot of things, I think that's actually the limitation of conventional software, conventional machine learning, deep learning. For now, the large language model actually open a new domain, a new door for us. I think you incorporating language model into software development will be the next big thing. I see a lot of startup company they're actually using LLM to directly create generate test cases, generate the code, generate the architecture, a lot of things the traditional approach cannot be done. They're now do better even than human being.
Yeah, that's a very good thing that you started this conversation in terms of other companies. In case someone is listening us and wondering where to start their deep learning journey, what would you recommend first to read, or maybe YouTube channel or research papers or anything that you would prefer to start if you were on
I
that
would start
case study?
from suggest people from first of all familiar with the libraries. For example, studying there's a lot of tutorial regarding TensorFlow and PyTorch online. People can start from there. Even the TensorFlow and PyTorch, their website also give you a lot of tutorial for the beginner and experts. And then reading paper will be another good way for advanced learning.
And in terms of the skills that are supposed to be in place for the companies who are companies are going to implement such activity and new functioning new functions into their software, what they should take care about in terms of hiring people, what skills people should have to be able to work with this system. So you said about the libraries, maybe some particular programming languages.
Yeah,
Is
this
only Python is used for this, or maybe other languages are also applicable in this case?
I think your question is very quite interesting. So when we look at the machine learning libraries, for example, as the table show here, so you can see a lot of the machine learning library, they're not actually developed from an engineer perspective. They're developing the library from machine learning guys. So they really like the engineering perspective. So I think if you want to incorporating machine learning, deep learning into your product, you should hire people who have the visions from both machine learning and engineering. It's better to hire a software engineer who know machine learning, not to hire people who are machine learning but do not know engineering side. Right. So we're building the product. The product is more about building things that are usable, reliable. Not only work. Work is the lower bar. Above work, you should consider usability, reliability, security, right? But if you look at the machine learning libraries, those machine learning guys, they only focus on the functionality. There's a lot of non-functionality things have not been considered. Yeah, we also have another study to explore the non-functionality issues in those libraries. We're still working on that.
Okay, then good luck. Good luck
Thank you.
to all employees, and good luck to all companies searching into like talented people in this field. Just
Yes.
one more.
I would like
Yeah,
to go
sure.
back, jump back
Yeah,
to
please.
the previous questions that we discussed on defects prediction and explainability about it. I think there is a constant debate on the trade-offs between efficiency and explainability. So if we can see that historically something is capable to predict where problematic code. So if we look at historical code and then discover that there were problems really obtained in this code, can it serve as justification for the absence of explainability? So we can say, yes, so we are not able to produce human readable text that describes why we selected this particular code as problematic. But if we look historically, we can see that it predicted. So efficiency is there, maybe not explainability, but efficiency. So what do you prefer, for example, for cancer treatment, something that will have higher percentage of detecting, or something that will always provide a clear description why it selected it?
Yeah, I think the performance and the explanation are both important, but from a more actionable perspective, the developer want to know more about the explanation. Because as I said, if you say, "Oh, your code there's a bug in your code," and then if you do not give explanation, how come I gonna find where the bug is? How to detect the bug, right? So the traditional conventional deep learning modules is lack of the capability to provide an explanation. Yeah, but for now, within the large language model, I think we're able to do so. Yeah.
word.
Yeah, I wanted to. I'm sorry, we're constantly following up in other questions, but going back to the skill set and for deep learning libraries, we have one more question from the audience in LinkedIn asking, probably someone is looking forward to select the university, and they're asking whether you will recommend going to York University. I'm not sure what the end goal of the what the angle of the future work job that is asked, but maybe it's in research field as well, or maybe IT.
So for our colleagues in Toronto, probably they have kids looking into possibility to go somewhere. What do you recommend York University?
Yeah, York is expanding in recent years, and then we hire more than 40 faculty members in the last 2 years, last 3 years. We're expanding. Regarding software engineering and AI, we're a gaming player in the market. We have a largest software engineering research group in Canada. And then if you look at our publication every year, we have more and more top tier publication. And then we also did a lot of great work on SE and SE plus AI domain. We actually host a seminar on SE and SE plus AI domain. We invited a lot of experts from industry and academic to give a talk every month. And then if you want to apply, yeah, you're welcome. We have a lot of position for PhD, master, and we're even opening another MEng program in the next. I think maybe next year we're gonna open the MEng program for industry people who want to empower who want to learn the machine learning and SE things. We have a new program. It's gonna be 1 year program for master. And then if you want to do research, we also have a thesis-based and PhD-based program. And then, yeah, we have a lot of good faculty members to choose.
Sounds very exciting. I think that it was a very good marketing for York University. Thank you very much for that. So regarding your research and your work that you have shared right now, what are your plans for the nearest future in terms of the research? So you mentioned in the end you have two directions that you've been releasing. The paper have been released regarding RAG, right?
Yeah.
And direction
Fine-tune.
1 and 2, right? Mm-hmm.
Yeah, I think
so you're going to continue with this?
Yeah, so we're actually doing fine-tune now. We're fine-tuning small large language model, not a big one. For example, ChatGPT, they claim open source, right? They're not open source anymore. You're not able to access to their source codes, right? So we want to fine-tune our own one. And also we find for software engineering tasks, it's not necessary to use in the state of art. Even for task generation, fine-tuning a small one is enough. So it's gonna save you a lot of time, a lot of energy, and a lot of money. We're not only fine-tuning. I think fine-tuning, for example, Code Llama 7B is even better than ChatGPT 4 on code generation. Fine-tuning is one of a very efficient way to increase the performance of small large language model. And then another direction, as I said, is RAG. We also work on building different RAG for different software engineering tasks. That's going to be the main two direction we're gonna do in the next few years.
Thank you.
Doing this kind of research, do you have any view on the temperatures that should be used in LLMs when we are trying to use them in software testing? Should we try to make it more deterministic, less deterministic, or there are trade-offs in these areas?
That's good. I prefer to make them more non-deterministic to cover corner case. Yeah, because the purpose of testing is to find the bugs, right? So to cover more code. As the more non-deterministic, the more corner case we're gonna to cover, I think.
Sounds good. Yeah, reasonable. Thank you.
Cool.
Let's see. So I'm conscious about the time. I think that we covered the questions from LinkedIn. And Yosef, do you have any other questions?
No, thank you.
Yeah,
Um,
yeah, I have one message.
It was really interesting
Thank you,
and
Professor
insightful
Wang.
presentation. Yes, I hope it will be very useful for anyone who participated, and we also will upload it to both LinkedIn and YouTube, so people can listen, watch, and to get inspired by your work. It's very interesting. Thank you.
Thank you very much. And I think we're
Thank
currently
you.
open to collaboration. And if you want to collaborate, feel free to let us know. We can do a lot of different type of collaboration, either from the Instagram or NSF. There's a lot of funding we can apply. We can also send students for internship if you want. Yeah.
Sounds
Thank
very
you,
good.
Professor Wang.
Thank you.
Sounds very good.
Cool.
I hope that everyone who listening us on LinkedIn will continue their research. We will share definitely the presentation and the links to all the research papers that been mentioned during the webinar. And stay tuned for the updates and follow us on LinkedIn, X, and YouTube channels. And I hope to see everyone on our next episode on AI testing talks soon. Thank you very much and bye.
All right. Thank you. Bye.
Bye bye.
Thank you very much.